to forget you, so I get alone in my bedroom. I hold up the mirror against you. I fight up with ways to regret you.
Okay, so last stream I wrote this server called IO server as part of reading the chapter on alternative IO models. I wanted to set up this IO server to basically just bounce IO back to me. So if I do vim on this, this is a high level overview of what it does. It binds and listens to a port and then creates a thread that dispatches that port, and then it has in the main thread it blocks handling input. So the handling input goes into a for loop reading forever, and every time it does a read, the read blocks every time it does a read, and then parses out different commands that you can run. These commands set the socket state on the file descriptor that you provide, and you can also print out all the state of all the file descriptors. State is a global up here. Keep on going up, 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 up. Here it is, connection state. There's a init con state, which I should probably pull up closer to the place that it's located. I feel like those should all be located near each other. So all this is connection state stuff. Basically it reads the soft R limit for the amount of file descriptors and creates a array of integers for every file descriptor. So the state is basically one integer for every file descriptor, and then using that integer we can communicate different states that the sockets, or that the server should behave in based on the socket that it's operating on. So that was down here. So that was all the handle input. So basically the main thread is in a infinite loop reading input from standard in that you can type in, and then dispatching commands to update the global state. And then all the sockets that were accepted then monitor that global state and change their behavior based on it. So the main thread here that was spun up to handle the client connections was this dispatch here. And I guess because, yeah, so the yeah, okay. So dispatch goes into an infinite loop, accepting connections, and then spinning up a thread to handle those connections. And then this handle con here goes into an infinite loop of its own. So the main thread is in an infinite loop that monitors standard in for commands. So it is not an active loop. The dispatch loop is monitoring for accepts, so it's blocked on that, so it's not active. And then the handle con, it's semi-active. So it's not aggressively polling, but I set this option on the socket up here that will time out the any IO operations after receive time IO. So not send time IO, but receive. I guess I should set it for send as well, right? Nah, don't have to worry about that. Well, trying to think. Yeah, let's send it for send as well. Send time IO, SORCV, SND, not SEND. always hate how C like pulls out vowels and does weird stuff with names. It's just like so like annoying. Anyways, so now we're gonna do suck op here for both of these sockets. Those return an integer. Should probably be asserting that, right? Or at least it's saying like, okay, if I can't set it, then I'm gonna exit early, right? Let's assert it. So it's man to set socked opt. I think it's a syscall, yeah. And then return. Return, please. On success zeros, return for standard. So we're just gonna assert that it's greater than or equal to 0 on those two calls. So assert ret. Oops. Maybe you guys say int ret. Assert that ret is greater than or equal to 0. And we'll do the same thing with this call here. Ret. Bam. Okay. Alright, close out of that. So this guy, all of the client sockets. So I guess to explain this, after you accept, you have like a peer. I guess you would say a peer file descriptor that is the peer socket. And once I have that peer socket, I set these two options that make it to where the I/O that it performs will time out after 1 second. So it will block, but it won't block for a long period of time. So it's kind of like polling, but it's like not as aggressive. And then reads the socket state. So remember, the state is what's being communicated from the main thread to the sockets, the peer sockets. Resets its error no so that it can report it appropriately later on. It's the thread local. And then switches on the state. You can set it to 1, in which case it's just going to take a little bit of a nap for 1 second. And then case 2 is for writing. Sorry, I need to turn my alarm off. I'll be right back. My alarm to get off the computer. But I'm getting back on. Alright, so case 2, we basically do a single write. So as soon as we enter the case, we set our state back to 0 so that we continue doing reads after the write. And then we just do a simple write here and then break. The reads, so this is going to block again for 1 second. If the end is 0, that means we're at EOF, in which case we go to cleanup. Down here, we just say I'm closing the FD, close FD, and then return null. Here, we say if error no is E again, which means that the read operation basically timed out, we then just continue. So this is kind of like an semi-active I/O, because it's waking up, doing its sorry, it's not waking up. It's performing its read, getting descheduled off the CPU. The timeout happens. The kernel then reschedules it, gives it the E again. It does a continue. The continue then pulls the state again, goes back into the read. So we're constantly every second coming out of the read, going back up the read. So we're spending a small amount of time on the CPU, but it happens every second. So with enough threads, it's going to be a lot of like noise from that. So ideally we wouldn't be doing this. Ideally we would be monitoring using select or something. So I think eventually I'm going to modify this server to do that. Or using some type of like semaphore to communicate, not semaphore, condition variable to communicate that the global state has changed. So right now it's a bit bit noisy. We'll say that. But the intention is to have this IO server have a client, the app thread, make multiple connections to it, perform IO with it, and do that in different methods, and blocking, non-blocking, and using like ePOL and stuff like that. So that's the intention. So I guess we should continue reading the chapter. I do have a to-do MD for implementing some other stuff here. Oops. Let's quit. Let's go ahead and open downloads PDF. Move that over here. Move this over here. Okay, I'm just going to continue reading from the start because we didn't get very far before I started playing with this server. Most of the programs that we have presented so far in this book employ I/O model in which a process performs I/O on just one file descriptor at a time, and each I/O system call blocks until the data is transferred. For example, when reading from a pipe, a read call normally blocks if no data is currently present in the pipe, and a write call blocks if there is insufficient space in the pipe to hold the data to be written. Similar behavior occurs when performing I/O on various other types of files, including FIFOs and sockets. Disk files are a special case because of the buffer. Okay. The traditional blocking I/O model is sufficient for many applications, but not all. In particular, some applications need to be able to do one of the following. Check whether I/O is possible on a file descriptor without blocking if it is not possible. Monitor multiple file descriptors to see if I/O is possible on any of them. Well, checking whether I/O is possible on a file descriptor without blocking if it's not possible. You can just do that with non-blocking flag. Monitor multiple file descriptors to see if I/O is possible on any of them. That takes select. We have already encountered two techniques that can be used to partially address these needs: non-blocking I/O and the use of multiple processor threads. We described non-blocking I/O in some detail in section 5.9. 44.9, if we place a file descriptor in non-blocking mode by enabling the O non-block open file status flag, then an I/O system call that can be immediately completed returns an error instead of blocking. Non-blocking I/O can be employed with pipes, FIFOs, sockets, terminals, pseudo-terminals, and some other types of devices. Non-blocking I/O allows us to periodically check or poll whether I/O is possible on a file descriptor. For example, we can make an input file descriptor non-blocking, and then periodically perform non-blocking reads. If we need to monitor multiple file descriptors, then we mark them all non-blocking and poll each of them in turn. However, polling in this manner is usually undesirable. If polling is done only infrequently, then the latency before an application responds to an I/O event may be unacceptably long. On the other hand, polling in a tight loop wastes CPU time. In this chapter, we use the word poll in two distinct ways. One of these is as the name of the I/O multithreading system called poll. The other use we mean is performing a non-blocking check on a status of a file descriptor. All right, so I'm trying to think like what type of tests do I want to do to exercise these ideas. So I want to have concurrent I/O. So let's go ahead and write our first client. I'm just gonna let me move this over here. All right, so let's write our first client. And the idea is that we want to send data to the server, and we want to monitor how much data we're sending. So, boom, 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 boom. Let's do the basic unit of concurrency that I'm going to start with is threaded concurrency with blocking I/O. Blocking threads dot c. Okay. And basically we're going to pthread up 3 connections. Each one of these clients is going to establish 3 connections and then monitor its own rate for data transfer. So I'm going to establish a global unsigned integer, uint64t, and this guy is going to be byte count. It's going to be a global, which means that we need a mutex, and it's going to be initialized to 0. And then we have our mutex here, which would be our byte. We'll say a pthread mutex t, byte count. Actually, no, we can just do atomic operations on this thing. I don't know how to do that in C, so we're going to learn how to do that. If I have a global counter, how do I perform atomic adds on that counter in C? I think it uses volatile. Oh, it's an atomic type. C++11 has underscore atomic. Standard atomic.h, that's C11. So you can do increment, which has these functions that you can apply to the counter, similar to Go. You can also use atomic fetch sub, atomic load, atomic store, etc. These operations are lock-free if the platform supports it. GCC Clang built-in atomics. So you have your global counter as an integer. And then there's these functions called sync, fetch, add. Don't want to use a mutex. Under atomic, where's that coming from? There are newer under atomic built-ins which are more flexible. Under atomic. Why would I use C11 versus Clang GCC? What are the trade-offs? So it's portable. Okay, we'll just make an underscore atomic then. I need to add numbers to the counter and also read plus reset the counter to 0. Give me those two functions. It's called atomic exchange. Okay. Atomic. This is from standard atomic. Atomic fetch add counter n. Atomic exchange. Counter 0. Okay, I'm just gonna leave these here as comments for now, just so I don't forget them. So in our main, okay, what are we gonna do in our main? Spin up 3 threads. Each thread attempts to write data non-blocking or blocking we'll say 6 threads. 3 threads attempt to write data blocking. 3 threads just async read. Main thread blocks forever. What is the best way in C to block the main thread? I use pause, yeah. I like pause. Okay. Show the select example. Blocking using select was my favorite in Go, but this is a little bit more nasty here. So I won't do that. Okay, so we just pause. Okay, where's this? Man, pause. Unix standard.h. Okay, great. Unix standard.h. So we're going to do a pthread create. So we're going to have a func called reader and a func called writer. I think these are void stars, and they take in an arg, void star arg. I think that's how the pthread stuff works. Return null. Oops. Return null. Okay. So let's go ahead and do our pthread creates. So we want to say pthread, sorry, thread t, and here we'll do for well, we got to read and write in 2 separate threads. So I'm going to say for int I is equal to 0, I is less than 3, and then the C way of doing it is plus plus I. I don't know why. So it's pre versus post decrement. Okay, so we got our I. Do we even care about I? No. So here we're going to say socket, and to we pop up an IO server, we can grab our headers here for socket programming, which we're going to need here. Okay, so now in here we can say, hey, socket, and our domain is going to be, what is this? iNet? What's it called? iNet? Can never remember these flags. Socket. Where do we actually create the socket? Here it is. AFINet. I would have remembered that. AFINet. The type will be sock stream. And 0 is the protocol. So we're going to say FD int. I think it returns an int, right? Yeah, int. Assert that FD is greater than or equal to 0. Okay, so we got our socket. And now we're going to do our connect, our FD to our adder, which will say pointer adder. And then this will be size of adder. And then if we man up connect here, it's returning an int. Return. Okay. We'll just say assert that ret is equal to 0. And we'll assign this int ret is equal to connect. Now we have to create our adder structure, which we can do just by copying this. That's the reuse adder thing that we don't need, yeah. Okay. So we say iNet on the port from argv. We'll get that from argv. So we'll say argv, this guy. There we go. Let's put that in the main here. So this is a knitcon state. I think we're good. Yeah, we don't need to do anything like that here. I'm gonna need assert.h. Okay. And I need this. Where is a to I? Man a to I. Which in libc standard lib. .h. Okay. Connect. We need to have this be this would be in adder local loopback. There we go. In adder loopback. Okay. Why is this thing complaining? Let's kill that. Kill that. Think about types socket adder. Oh, I need to do the type conversion on this, or type assertion, which is a struct in adder, I think it's called. Pointer. Something like that. What is this? Adder is a sock adder, sorry. Sock adder, pointer. Okay, so now that we're connected, delete these. We need to pthread up our reads and writes. So pthread t reader, we'll just say R here, and W, say they're both the same type. Then we pthread create pointer to read. Oops. I don't know how that got messed up. Pointer to read. Okay, I'm gonna have to go over here, say man pthread create. Okay, so we need a pointer to the thread, some adder struct, which I think can be null. And then we give it a reference to our reader. And then the argument will be I need to pass the file descriptor I want it to handle. So we're going to have to convert this to a specific type. I forget how to do this conversion. So let's jump over to IO server. So I've done it over here. Yeah, this guy here. Okay. Paste that there. Kill that. Close that. Close that. pthread create is going to need the headers for this, which is pthread.h. Yeah. I'm going to kill that. Okay. So now we pthread created our thing. I'm going to make this a little bit bigger. Just give us a little bit more room here. So pthread, oops, pthread create. We didn't assert this thing when we did our dispatch. It could have failed. So we need to assert here. Man pthread create, oops, create. This gives us back an integer. Success pthread create returns 0. So you just want to assert that. So ret is equal to that, and then we gotta say int here. Assert that ret is equal to 0. Okay. We'll do the same thing over here for a guy over here. And we already have a ret because we did our connect up here. Okay, so that takes care of our reader. And we want to do the same thing for our writer. So this would be W. Get the same exact argument. It also needs to have the right function pointer, which goes there. Okay. And then we assert that as well. We don't need to do that. Okay. Okay, our reader and writer now. So they reader will just do blocking reads. It's fine. I guess everything's gonna do blocking on this example. So this one, we go into a forever loop, and oops, come on, stop it. We do our reads, which I can just go up to here and copy the reading code from here. Where is it? Here it is, the default. Boop. I don't need to do all that, but say int n read from fd. Fd we need to get from here. Boop boop. So do fd, read from fd into our buffer. Buffer, we'll just allocate it here. And it's fine. Then we go to cleanup. N means that you're done reading. I'm curious, with sockets, can you have a half closed socket where one direction is closed, half duplex, using shutdown? Oops. Okay, so the reader won't, we'll say here, note the reader doesn't close the FD on EOF in case shutdown was used. We just return null. And we don't need to do a cleanup, so we can just say return null here. That's fine. If it's E again, which it should never be, we just continue, but pretty sure it doesn't. Will never be that. Error no. And then here we just say, hey, we read some data. We'll print it out, which means we need to reset our error no before we perform the read. Okay. So read is what is this thing called? Complained about? Call to undeclare stir error. Where's stir error? Thought that'd be an error, no. Maybe Unix standard.h? No. IO server. Let's see. Maybe string.h? Seems like a weird one. No? Okay, I'll just look it up. What's it called again? Stir error? Man stir error. String.h. It is string.h. Then why did that still error? We got 123 string, 123 string. Called to undeclared, like, oh, because standard IO is not declared. Okay, IO, there we go. Alright. So basic reading functionality is there. Alright, now we do our writer, which will be more involved. So our writer needs to perform writes. Oh, and we need a reporter too. Maybe our main thread can report instead of pausing. Say to do report from counter. Yeah. That would be a good thing for the main thread to do. So we're going to perform writes, increment or add n to global counter. That's really all it's doing. Oh, and close FD when done. Not that you really need to do that in this situation, but it'd be nice to have the writer be responsible for that, even though we're just going to kill the process anyways. Alright, so what's going on here? We're going to need some of this stuff. Oops. So let's grab this. I kind of want to fill the buffer with random. Give me the C code to create a buffer on the stack and fill it with data, with random data bytes. What does this use? Rand function, okay. I don't really care about seeding it, to be honest. Okay, so here we're just going to fill this with random data. It will make this thing like maybe like what? How big do you want to make this? 10K? Maybe 10 megs? So that'd be 2 to the power of what? 20 would be 1 meg. And then we'll say 10 times that. And so we quit that. Let's go to say Python. If we say 10 times 2 to the power of 20, so it should be 10 meg, or yeah, it should be 10 megabytes. 20 megabytes. 10 times 2 to the, Sorry, 1 to the power of 20. There we go. I don't know why I did 2. 1 to the power of 20. Okay. We'll say buff. This is buff size. Pound define buff size. That buff size, and then we say okay. Okay, cool. I don't need this comment here. It's kind of useless. Okay, so now we got our buffer filled with some random data. We say forever. We are going to do our write. Let's kill this. There should be a write syscall here in our switch somewhere. Switch, IO server. Switch, here we go. Let's do a write here. Pretty straightforward. So we got our file descriptor, we write our buff, and our n is 14. No. This will be buff size. Buff size, bam. So that's for n. Right to our guy there. And then we want to like handle our error cases here. So if I guess we don't really care. We say if n is equal to 0, then we can return go to cleanup. So this will be EOF. And cleanup down here will be to close the FD and return null. And we'll do our low printf as well, why not? Boop. We need to add to our global counter. So regardless of what n is, and this is negative, let's see, man write, return, oops, man to write, return. On error, -1 is return. Okay. If n is less than 0, then we freak out. This would be a write. Okay. We need to set our error node here on each loop. So that's set correctly down here. And if we got all the way through this will be a continue. It's like, oh, hey, we got an error. I'm going to continue. Actually, you know what? Let's go to cleanup on that as well. Whenever writes fail for unexpected reasons, we'll go to cleanup. And then down here we say this is where we need to do our atomic fetch add. Our counter is going to be byte count, and n is going to be our mount. And I want to man that. So man atomic fetch add. Oh, okay, no documentation for that. Wonder if AI hallucinated it. Where do I find the documentation for atomic fetch add, since I don't have man pages for it on Arch Linux? Man std atomic? No. What's going on here? What's going on here? I don't like C++ references. Give me the pacman command to add them. I already have that. glibc docs? Okay, I'll try that. glibc docs. There's no glibc docs, brother. Let's kill that. So I guess this is C, and that's this C++ version. So I want atomic add, not fetch and add. I guess all adds are fetch and add. What's explicit? Okay. Kill that, kill that. I'm gonna kill this as well. And then we can bring this back over. Okay. So, fetch and add, but we're gonna throw away the value. That looks good to me. Alright. And then here we're gonna go forever. We're gonna sleep every second. We're going to use our atomic operation here. Actually, who needs this byte count? I'm gonna move this down further. I guess it can't go down too far. Okay. Let's go down here. So atomic exchange counter is this to be byte counter. And we're then going to say print f, and this will be our rate, which will be have to ask AI here. in C print integer in human friendly format. I don't care about set locale. Okay, whatever. Do that up here. Then printf here will be percent d like that. And it'll be what? The n that we read. Or v, int v. V. I'm not going to do that then. So I guess on the locale. This thing's complaining because byte counter. Is that not the name of it? Byte count. Not counter. Okay, so that's going to loop every second. It's going to reset the counter and print out the counter, and I'm going to say per second. Bytes per second. Or just say bytes per second. And I'll do a /t here to tab it out. Okay, make build IO server 1, 2, 3, 4, 5, and then over here, jump to chapter 63, build, this will be blocking threads 1, 2, 3, 4, 5. Okay, we got a segmentation violation. So we got some problem. Can we run it under GDB maybe? Maybe it's like this. Ptrace no such process. Okay, let's see. How do I run GDB and have it exec a new process with args? To do set args, so ugly. I can see dash dash args. Okay, let's try that, dash dash args. That. Okay, so it happened as soon as I hit restart. Ret 0 fill, sig program received abort, sig abort. That wasn't the oh, because I couldn't connect. Okay, well, we'll go up here and run the server here. Build 1, 2, 4, 5. There we go. Oops. IO server. What is it called? Jump to chapter 63, not 23. And then run build IO server 1, 2, 3, 4, 5. There we go. I'll throw you over here. So we care about that. Now we can do this. Okay, so now it gets segmentation vault. Thread 3 blocking thread. Received. So be the writer here. Let's comment that out. Make well, let's go ahead and do this then. How about we just don't create any threads and we just report the counter? Make sure that works. Make this guy. Yeah. So that's working. And then if we pthread create our reader, quit. And then we say make, do this again. Okay, so our reader is, it's really that writer that messes things up. So we got our W here, writer. And we're just going to take away this fetch add. It's the only thing I can think of that might be messing it up. Also, I guess maybe if I messed up the argument, no, it can't be that because the reader is doing fine. Okay, quit, and then make, rerun, no, restart. Okay, so still got the segmentation fault. Huh. What could be causing this? Well, I'm going to comment out everything and just return null. Okay, quit, yes, make, no. Okay, we have our three. So it's something in this body that is messing things up. Okay. The go to cleanup. Maybe it's this printf here. Make. Okay, we still got a segmentation fault. Stack. Backtrace. So it's in the writer somewhere. Come on, what are you doing here? Okay. Quit out of this, yes. Vim makefile. And we're going to go down to our C program. And we're going to say, hey, I'm going to enable G00. Let's see, make clean, make. All right. $41. Well, that's just a function. Oh, it got 0. It got null? How? How did this guy get null? It's the same exact file descriptor that we gave to the reader. Arg is 0x0. If we print out our FD, it says 0. Sorry, pbuff. Okay. P error, no? Oh, that's because it's not even on the stack. Vars, locals, stack, info threads, okay. Three, which is writer. BT full. Info locals, okay, info locals. How is FD 0? How is that possible? Okay. Yeah, read and writer are both 3. That's right. So that's not the segmentation fault. I think maybe the stack got messed up on this thread because it was not 3. Okay, we'll just do a little println debugging here. Printf, we'll say pre-write, and then we'll say post-write, pre n is equal to 0 cleanup. We'll say pre n is less than 0 cleanup. And then that's it. Then here we'll just say we already got the printf there. So quit here, yes. Make this. So pre-write. So the right segmentation faulted. Passing, oh, it's because it's a pointer to a buff, like that. Oh, yeah. Makes sense. Make. No? Make. The error now? Oh, the buffer size is too big. We have to malloc this thing. Okay, that makes sense. Okay, so void star, we'll call it a char star. Buff is equal to a, we want to malloc buff size. It's because we were stack allocating it and it was just like way too big for the stack. Okay, so we got a malloc buff size, man malloc. I think that's all I need to do, right? Yeah. So down here I'll free it as well. For a free buff. So you malloc it up. It's a pointer already, so I just pass it into right like that. Okay. Make that now. Make. We'll just run it. Hey, look at that. Bunch of garbage here. We don't need anymore. We can initialize the memory now. Make. Let's go and run it. It's doing a lot of reads, but it's not incrementing the counter anymore because, sorry, I need to restart that. Because I commented this out and did that as well. Okay. Let's do make. There we go. Hey, look at that. So we're getting 200 roughly megs. Between 3 threads. I wonder if I can increase my thread count. Why is my read so small here? I need to fix that. Let's go to IO server. When it's performing its reads in that switch. So it's reading its buffer here. This buffer needs to be way bigger. So here, this can be a little local buffer here. We'll call this small buff. Small buff. Oops. Small buff. Okay. And then up here we're going to malloc up our huge buffer, which if I go back to my blocking threads would be this thing here. IO buff size. We're going to paste this here, and then we'll change the reference here. This would be in buff size. Oops. Here we're going to malloc up buff size. And we're going to say, hey, buff, you're going to be a char star. You go there. Okay. And then we read that into buff, which is already a char star, so we don't need to pass in a pointer here. Same thing with right here. Okay. Size of buff. The read, I don't want to printf here because it's just like, actually no, that was very helpful that I saw that it was a very small amount of reads going on. Oops. Let's go ahead and make, rerun. Let's rerun this. 8. No way. No way. Okay, please stop. Please stop. Alright. So we changed the buffer to be 10 megabytes. And it started being like going crazy, saying I only read 16 instead of. The other thing it changes is random data. So maybe we just not do random data. Blocking thread. Let's just not do that for now. Let's do make. Nope, that wasn't it. Wow. Okay. Why would IO server be slowing down here? Oh, because it's size of buff instead of buff size. Buff size here. Okay, that makes sense. Actually, let's bring back our random data here. Kill that, bring that back, run that. Okay, now we're getting somewhere. Negative? There's no way. Why is it going negative? Maybe because it doesn't know that it's a uint. With C atomics, how do I perform operations on a uint? Oh, let's say atomic uint. Do I? Alright, let's go back over here. Paste that. Wrong type for V. Atomic exchange returns the same type as the atomic object. Oh. Okay, that makes sense. So I need to say uint 64t. I mean, it kind of makes sense, but not really. Why is it all negative? Maybe n needs to be n is ever negative. It wouldn't be negative though, it would always be positive. Oh, maybe it's let's do maybe just D. The hell? I'll do a long U. Maybe that will help it. Make. There we go. So we're getting 200 megs before. Now we're getting, so that's K, 51 gigs. Well, that's a lot. So that would be 3 there, meg, about 50 gigs per second. A little over 50 gigs per second. I wonder if we increase the amount of threads. How many cores do I have? Not Etsy, proc, CPU info. Sorry. So this would be processor, core ID. Let's do core ID. Cat grep for, oops, core ID. It seems like I have 16 cores. So if I increase this concurrency here, let's see. Sorry, that's the wrong one. We want blocking threads. Delete that comment. So in here, we do 3. So this would be a pound define num threads. 0 is 16. Say 16. Num threads. And then we'll do a make. Oops. Make. And we'll do our this guy. Wow. So that is KM. We got to 134. Jesus. 134. What if we did like half that num threads? Maybe we did 8 or 10. But that's still crazy. So that's KM 134. Let's make. Yeah. And then if I do make, yeah. Let's change this to be 1. So this is actually KM16. So it seems to go up linearly up to maybe, let's see, it went from 16 to 100, was it? 16 gigs to 100 gigs? 150. So it seems like I can go up to 10. And then it starts being diminishing returns. So yeah, about 150 gigs. It's pretty crazy how much bandwidth you can get over just your memory. So that's 150 gigs. Alright, so that's a blocking threaded. And then I want to do some experiments here where, let's go ahead and rerun this guy. And then we'll connect a bunch of stuff here. We'll just print out the status. And then maybe we start blocking some stuff here. Why is that going down? I could say block 20, block 19, block 18, block 17, block 16, block 15, block 14, block 13, block 12, block 11, block 10, block 9. Print out everything. Unblock 9. So my CPU fan just turned on, which in my mind might mean that this IO server is not sleeping enough. But if it's blocked, then it's going to sleep for 1 second. It's doing a lot of sleeping. Block 9. Still only 31. It's still, oh, there, we just got above it. Okay. It can crank through a lot of data here. Alright, well that's the blocking threaded model. $139. I think I had some more impressive numbers. 160, 184, 200. Oh, that's the wrong one. We'll just rerun it. $160 roughly. So that's 160 gigabytes per second. Kill that. All right. So what would non-blocking threads add to the mix here? We could say, hey, don't block. Which will mean that when you can't do writes, you'll still remain on the CPU. I mean, I don't even see a benefit in doing like non-blocking threads. Because it just means that the threads are going to be staying active on the CPU. Which gives us no benefit whatsoever, really. I mean, I can do it. You just have to set the O non-block flag or whatever. What is it? The file descriptor here on the right side, maybe. Give me the C code to set non-blocking mode on a socket for writes. Yeah. Okay. Just go up here. So the writer is gonna need FCNTL then. FCNTL. Assert that flags is greater than or equal to 0. Okay. Let's go ahead and make. So now we should be able to run non-blocking threads. And we'll just add some carriage returns here. About the same. Okay. Let's continue on with the reading here. Now that we have those two clients, test clients written. Alright. If we don't want to process a block when performing I/O on a file descriptor, we can instead create a new process to perform the I/O. The parent process can then carry on to perform other tasks, while the child process blocks until its I/O is complete. If we need to handle I/O on multiple file descriptors, we can create one child for each descriptor. The problem with this approach are expense and complexity. Creating and maintaining process places a load on the system, and typically the child process will need to use some form of IPC to inform the parent about status of I/O operations. Using multiple threads instead of process is less demanding of resources, but the threads will probably still need to communicate information to one another about the status of I/O operations. And the programming can be complex, especially if we are using thread pools to minimize the number of threads used to handle a large number of simultaneous clients. One place where threads can be particularly useful is if the application needs to call a third-party library that performs blocking I/O. An application can avoid blocking in this case by making the library call in a separate thread. Oops, there we go. Because of the limitations of both non-blocking, let's see. Because of the limitations of both non-blocking I/O and the use of multiple threads or processes, one of the following alternatives is often preferable. I/O multiplexing allows a process to simultaneously monitor multiple file descriptors to find out whether I/O is possible on any of them. The select and pull system calls perform I/O multiplexing. Signal-driven I/O. This technique is a technique whereby a process requests that the kernel send it a signal when input is available or data can be written on a specified file descriptor. Process can then carry on performing other activities and is notified when I/O becomes possible via receipt of the signal. When monitoring a large number of file descriptors, signal-driven I/O provides significantly better performance than select and pull. The ePull API is a Linux-specific feature that first appeared in Linux 2.6. Like the I/O multiplexing APIs, the ePull API allows the process to multiple monitor file descriptors to see if I/O is possible on any of them. Like signal-driven I/O, the ePull API provides much better performance when monitoring a large number of file descriptors. In the remainder of this chapter, we'll generally frame the discussion of above techniques in terms of processes. However, these techniques can also be employed in multi-threaded applications. In effect, I/O multiplexing, signal-driven I/O, and ePull are all methods of achieving the same result. Monitoring one or commonly several file descriptors simultaneously to see if they are ready to perform I/O. To be precise, to see whether an I/O system call could be performed without blocking. The transition of a file descriptor into a ready state is triggered by some type of I/O event, such as arrival of input, the completion of a socket connection, or the availability of space in a previously full socket send buffer after TCP transmits queued data to the socket peer. Monitoring multiple file descriptors is useful in applications such as network servers that must simultaneously monitor multiple client sockets, or applications that must simultaneously monitor input from the terminal and a pipe or socket. I'm going to take a quick bio break here. I'll be right back.
It's hard enough to feel the uproar. I wish I didn't let you so close. With you gone, I could see the now I just wanna It's hard enough to find. To forget you, so I get alone in my bedroom. I hold up the mirror against you. I fire up the ways to forget you. Now I just wanna get back It's hard enough to feel the I wish I didn't let you so With you gone, I could see It's hard enough to find. I wish I didn't. With you gone,
I was just thinking that I should probably start changing the implementation of the servers instead of the clients. Before I was just like, oh, I just want to test like doing reads and writes. It doesn't matter if it's the server or the client. But if you think about it, most clients have an abundance of resources. They're not resource starved. So they can create as many threads as they want to do whatever concurrent IO they want. And it's usually the server that's the bottleneck. So all these performance improvements in IO are like focused on the server. And like yeah, I guess what I should do is I should have some type of benchmark, a consistent benchmark like AB or Siege or something, and like actually handle real requests even if I just 500 all of them or just 200 all of them, like actually receive real requests from like an HTTP test suite, benchmark suite, and then have it manage like the concurrent clients, and then have the server do its thing. Even then, it's not like super accurate because the clients and servers being on the same machine, the client's going to eat into the server resources. It's just inevitable. But like having a consistent benchmark, I could try out different server implementations and then see which one performs the best. That might lead to a good result. All right, let's finish up this section. We didn't get very far today in this chapter, but I did do a lot of coding, and so I feel like I'm getting my hands dirty with like the nuts and bolts of this stuff. I'm gonna go ahead and gonna kill the server here, and I'm gonna rename this mvio server to threaded server.c. And this is like we might need to change the implementation of the server as well. MV non-blocking threads to non-blocking threaded client. MV blocking threads to blocking threaded client. Vim, oops, please go away. Vim results. Yeah, I think that's good for recording the results that we got there. Okay. Let's pull up README here. Okay. So let's do a little bit more reading, and then I'll call it a night here. Let's say, in effect, I/O multiplexing, signal-driven I/O, and ePOL are all methods to achieve the same result, monitoring one or more commonly several file descriptors simultaneously to see if they are ready to perform I/O. To be precise, to see whether an I/O system call could be performed without blocking. The transition of a file descriptor into ready state is triggered by some type of I/O event, such as an arrival of input, the completion of a socket connection, or the availability of space in a previously full socket send buffer after TCP transmits queued data to the socket peer. Monitoring multiple file descriptors is useful in applications such as network servers that must simultaneously monitor multiple client sockets. Here's monitoring multiple file descriptors is useful in applications such as network servers, period. So there's nothing about clients here. That must simultaneously monitor multiple client sockets, so, but it doesn't say about using this technology for the client. Or applications that must simultaneously monitor input from a terminal and a piper socket. Note that none of these techniques perform I/O. They merely tell us that a file descriptor is ready. Some other system call must then be used to actually perform the I/O. One I/O model that we don't describe in this chapter is POSIX asynchronous I/O. AIO. POSIX AIO allows a process to queue an I/O operation to a file and then later be notified when the operation is complete. The advantage of POSIX AIO is that the initial I/O call returns immediately, so that the process is not tied up waiting for data to be transferred to the kernel for the operation to complete. This allows the process to perform other tasks in parallel while the I/O, which may include queuing further I/O requests for certain types of applications. POSIX AIO can provide useful performance benefits. Currently, Linux provides a threads-based implementation of POSIX AIO with glibc. At the time of writing, work is ongoing toward providing an in-kernel implementation of POSIX AIO, which should provide better scaling performance. POSIX AIO is described in so-and-so in the AIO man page. But IO uring replaced asynchronous IO. Which technique? During the course of this chapter, we'll consider the reasons we may choose one of these techniques rather than another. In the meantime, we summarize a few points. The select and pull system calls are long-standing interfaces that have been present in Unix systems for many years. Compared to the other techniques, their primary advantage is portability. Their main disadvantage is that they don't scale well when monitoring large numbers, hundreds or thousands of file descriptors. The key advantage of the ePull API is that it allows an application to efficiently monitor large numbers of file descriptors. Its primary disadvantage is that it is a Linux-specific API. Some other Unix implementations provide non-standard mechanisms similar to ePull. For example, Solaris provides the special dev pull file described in Solaris pull 7D manual page. And some of the BSDs provide the KQ API, which provides a more general purpose monitoring facility than ePull. Briefly, Stevens et al. Briefly describes these two mechanisms. A longer discussion of KQ can be found in Lemon 2001. Like ePull, signal-driven I/O allows an application to efficiently monitor large numbers of file descriptors. However, ePull provides a number of advantages over signal-driven I/O. We avoid the complexities of dealing with signals. We can specify the kind of monitoring that we want to perform, e.g. ready for reading or ready for writing. We can select either level triggered or edge triggered notification described in section 63.1.1. Furthermore, taking full advantage of signal-driven I/O requires the use of non-portable Linux-specific features, and if we do this, signal-driven I/O is no more portable than ePull. Because on one hand, select and pull are more portable than signal-driven I/O and ePull, while signal-driven I/O and ePull deliver better performance. For some applications, it can be worthwhile writing an abstract software layer for monitoring file descriptor events. With such a layer, portable programs can employ ePull or a similar API on systems that provide it and fall back to the use of select and pull on other systems. The libevent library is a software layer that provides an abstraction for monitoring file descriptor events. It has been ported to a number of Unix systems. As its underlying mechanism, libevent can transparently employ any number of techniques described in this chapter: select, pull, signal-driven I/O, or ePull, as well as Solaris-specific dev pull interface or the BSD KQ interface. Thus, libevent also serves as an example of how to use each of these techniques. Written by Niels Provost, libevent is available at so-and-so. Let's pull that up here. libevent.org. I don't see anything about IOU ring or even the POSIX, what is it? Or the Windows. I guess there's IOCP here. Okay. U-ring. Measuring. Okay. So, 1328 is where I left off, or I guess I say 29. And then I think I started today on the terminals chapter, right? Yeah, which is 1289. Okay, so I read 40 pages today. I mean, it's not an insane amount, but we made some progress. mainly on the terminal stuff, and then I wrote a bunch of programs. I'm going to need to write programs for this chapter to really get my hands dirty with like select, pull, epoll, threaded. I don't want to do like forking because that's like super slow. Like threads pretty much are just better forking. And then IOU ring would be a cool thing to experiment with at the end. But I'm gonna have to write several programs as I go along here, so it's gonna take me a while to get through this chapter. Probably all day tomorrow, and then maybe Monday we'll do terminals. But you know, I'm happy with the progress I made today. 40 pages, and wrote a bunch of programs in C. Did a few tests. Got 160 gigabytes of bandwidth through from a client to a server. So yeah, exciting stuff. I'll be thinking more about what we've done today. Just like as I sign off here, like in the evening, I'm going to be spending some time thinking about it. But I think the next step for me, obviously I want to read through the chapter to get that behind me. Let's see how many pages we got. Let's see, 1, 2, 3, 4, 6 pages. Some code, 7, 8, 11. So we got pretty much the amount of reading that we did this morning we have ahead of us. So what I might do is, instead of spending too much time writing programs, maybe I'll save up my ideas in like a document, and let's just read the chapter tomorrow morning, which is 40 pages. I can do that in the morning session. And then as I'm reading, write down all the things that I want to implement. And then at the end of the chapter, then we can experiment with implementing stuff. And there are exercises here, certain of it. Yeah. Oh no, that's the wrong chapter. That's pseudo terminals. Okay, here we go. Yeah, there are 8 exercises in the back of the book here. So if I don't have enough ideas of things to implement by the end of the chapter, I can just go through the exercises. So I think that's going to be the game plan tomorrow. Let's just get the 40 pages of reading done in the morning, get through the chapter, and then we'll spend all the rest of the day working on exercises and experiments. And then I think that would be sufficient treatment for this set of topics. Hey, how's it going? Yeah, I'm getting ready to sign off here. I was just kind of talking to myself about what I want to accomplish tomorrow. So tomorrow morning I'm going to sign on, finish reading the rest of the chapter on epoll, or alternative IO models. And then as I'm reading, I'm going to take notes about what I want to implement. And then the entire rest of the day after the reading is done is going to be playing with these APIs, experimenting, and then doing the exercises that are in the back of the book. Cool. Yeah, I really like it. I don't know if you watched any of the videos that DHH did on it, but he demos a lot of the stuff that's built into Hyperland, and it's pretty simple. I know some people are a little bit intimidated by it because it's like very keyboard driven, but yeah, I'm a big fan of it. I also might spend some time playing this lib event thing that he mentioned. I know there's another one. There's libuv that I want to play with. It's got a dinosaur as its logo. Asynchronous IO made simple. I want to see if they even mention IOU ring here. They don't in the docs. What about on the code? It's DU ring. During. So yeah, libuv is like another one I want to play with. So I might just spend the entire day tomorrow playing with different libraries that sit on top of these APIs, playing with the APIs themselves, doing some benchmarking, and doing the exercises at the end of the chapter. And that might even last me until Monday. I might even want to work on that Monday. But after this, after this alternative IO stuff, there's only one chapter and then some appendices left in the book. So we're getting close to the end here. What is the lib event? Lib event is something that he mentioned in the book, so it might be a little bit dated. If you go back here, he had a little blurb about it. But basically, it's like a layer on top of all these, operating system specific methods of getting notified when there's changes to file descriptors. So Mac OS and the BSDs have this thing called KQ. Linux has epoll is its primary mechanism. And then Windows has like I think it's called CPIO or something. But basically there's different mechanisms on different operating systems, and libevent is kind of like a library that sits on top of those interfaces and uses the ones that are appropriate. Oh yeah, and then devpoll and Solaris, that's another one. So these are the ones it supports. Devpoll, KQ, event ports, POSIX select, Windows select, poll, and epoll. And then it also does stuff for signals, I think. Yeah, signals and timeouts. So it's not just getting notified when there's when you can perform IO on a file descriptor. You can also get notified when there's signals or timeouts. It's pretty cool. All right, I'm starting to get really tired here, so I'm gonna hop off and get some sleep. But yeah, excited for tomorrow. Get some more programming done on this stuff. Cool. Have a good evening. Bye.